Welcome back to the Network Architecture Design Series. I'm Ray. In Episode 4, we're going to examine a common but often misunderstood problem: routing asymmetry. Many engineers spend hours adjusting routing policies and tuning BGP attributes, yet the problem never completely disappears. Why? Because the real cause may not be in the routing configuration at all. It may be in the architecture itself. This routing asymmetry issue we'll discuss comes from a real-world network we introduced in Episode 1. Let us start with a quick recap. This network consists of a headquarters in New York, 3 data centers located in New Jersey, New York, and Dallas, along with many branch offices. The headquarters is being connected to the 3 data centers. Unlike the headquarters and New Jersey data center that have dedicated WAN edge routers, Dallas data center doesn't have the dedicated WAN edge routers. Therefore, the WAN connections are directly attached to the distribution switches, DIST-1 and DIST-2, at Dallas data center. Historically, this enterprise network is called East and West. The Dallas data center belongs to the West. The New York headquarters and New Jersey data center belongs to the East. Historically, the East and West were 2 independent companies. Following their merger, East and West were connected via 2 WAN connections. One is from New York headquarters connecting to the distribution switch, DIST-1, at Dallas data center. The other is from New Jersey data center connecting to the other distribution switch, DIST-2, at Dallas data center. Engineers noticed that there is routing asymmetry issue between the East and West. For example, traffic from the New York headquarters to the Dallas data center is forwarded directly, but the traffic returning from Dallas to New York taking a different path. Engineers tried to turn the BGP policy to control inbound and outbound traffic, but the issue has never been fully resolved. Let's dive into this issue. Let's start with a question. Why has traditional troubleshooting failed to solve this problem? Traditional troubleshooting lives in a specific world: links, devices, configurations. It focuses the question, how? How do I fix it? How do I configure it? How do I test it? But what if the answer isn't there? What if the root cause lives in the design itself, not in any single device or config? Then no amount of troubleshooting will save you. You're not doing it wrong. You're looking in the wrong place. That's the shift we need to make, from troubleshooting thinking to architectural thinking. Architectural thinking doesn't start with how. It starts with what and why. For example, what is routing asymmetry? Why does the asymmetry issue happen? And here's the key insight. Once you deeply understand the what and the why, the how almost answers itself. What is routing asymmetry? Routing asymmetry means that when traffic takes one path from A to B, return traffic takes a different path from B to A. It is worth noting that not every different path is a problem. For example, ECMP networks, spine leaf fabrics. Redundant networks, return traffic may use a different physical paths, but it experiences the same latency, policy, and forwarding behavior. The paths are logically equivalent. Therefore, the different path is not a problem. The true routing asymmetry is that the forward and return paths are not logically equivalent. For example, forward, New York to Dallas. Return, Dallas to New Jersey to New York. Now traffic experiences different sites, policies, delays, and security devices. That is a true routing asymmetry issue. Regarding root cause analysis, RCA. Let's start with the effect and trace back to identify the root cause. Here, effect is the return path is different from the forward path. Forward path, New York to Dallas. Return path, Dallas to New Jersey to New York. Why doesn't the return traffic go directly back to New York? Why does the return traffic exit to New Jersey? Let's trace the return path to identify the root cause. First, is HSRP the root cause? Let us zoom in to Dallas Data Center. When a server sends the return traffic, it first sends the packet to its default gateway. The default gateway is provided by HSRP. If dist-1 is the HSRP active device, Dallas server to dist-1 to New York, the traffic returns directly to New York. No asymmetry exists. However, if dist-2 becomes the HSRP active device, Dallas server to dist-2 to New Jersey to New York, now the traffic becomes asymmetric. At first glance, it appears that HSRP determines which WAN connection to use, but HSRP only determines the active gateway. HSRP does not do routing decisions. Since WAN path is selected by routing table, HSRP is not the root cause. Let's take a look. Is the lack of a dedicated WAN router the root cause? Normally, WAN circuits terminate on dedicated WAN edge routers. But the existing network is connecting to the core or distribute switch directly. What are the advantages of dedicated WAN routers? Better routing and WAN capabilities, better traffic engineering capabilities, for example, ECMP load balancing, improved modular design, greater scalability and adaptability. However, no matter the dedicated WAN router is being used or not, the routing table remains the same. Since the WAN path is determined by the routing table, not by the device, the absence of dedicated WAN routers are not the root cause to the routing asymmetry.
Is routing table the root cause? Now let's examine routing in the two distribute switches, dist-1 and dist-2. The dist-1 and dist-2 at Dallas can receive the routes from east side by the EBGP. At the west side, dist-1 receives the routes from New York directly. Dist-2 receives the routes through New Jersey. Dist-1 and dist-2 are the same site and the same routing domain, therefore IBGP is built up between them. At the east side, New York and New Jersey both are part of the eastern region. They are treated as same routing domain. Therefore, the two sites share the same BGP autonomous system number, AS100, and IBGP is built up between them. As a result, the dist-1 receives the east routes directly from New York with AS path 100. The dist-2 also receives the east routes, but from New Jersey, also with AS path 100. For switch dist-2, it learns EBGP routes from New Jersey. It also learns IBGP routes from its peer switch dist-1, both east routes, both with same as path 100, but one EBGP, the other IBGP. Per BGP best path selection algorithm, the AS path is the same, so it's not used to determine the best path. Instead, EBGP and IBGP is used to determine the best path. dist-2 prefers its EBGP route through New Jersey over the IBGP route learned from dist-1. This explains why traffic exits toward New Jersey instead of crossing to dist-1 and returning directly to New York. But is dist-2's routing table wrong? The routing table simply executes the policies defined by the routing architecture. The routing behavior of dist-2 fully aligns with the design expectations. Therefore, there is nothing wrong with dist-2's routing table. It is not the root cause of the routing asymmetry. Let's see. Is BGP architecture design the root cause? Here, business views New York and New Jersey as two different sites. But BGP architecture actually treats New Jersey and New York as a single routing domain. BGP architecture assigns the same BGP AS100 to both New York and New Jersey, and build iBGP between them. As a result, the routing protocol at Dallas can't distinguish New York and New Jersey as the two sites. It leads the return traffic existing to New Jersey. As a result, the routing asymmetry is created. Therefore, BGP architecture is the root cause of routing asymmetry. But, is there any other root cause? Let us investigate the two paths between the east and west. Is the redundant architecture design the root cause? There are two paths between the east and west. One path is New York to Dallas. The other path is New York to New Jersey to Dallas. The two paths serves as redundant paths. They back up to each other. Architecture design principle requires that the redundant paths should be logically equivalent. If one is New York to Dallas, the other must be New York to Dallas. Then the paths are equivalent. If primary, New York to Dallas, backup, New York to New Jersey to Dallas, then the paths are not equivalent, and the redundant design violates a fundamental architecture principle. This design directly creates the routing asymmetry. It is the root cause to the routing asymmetry. In addition, the redundant path passing through the connection between two data centers, Dallas and New Jersey, which is actually passing through the data center interconnection, DCI link. Using DCI as a transit path for user-to-server traffic introduces additional complexity and contributes to the asymmetry problem. Why does the asymmetry issue happen? In our previous root cause analysis, RCA, we started from the effect and worked backward to identify the causes. In this section, we take the opposite approach. We start from the root causes and work forward to explain the effect. This is the approach commonly used in scientific research. A theory is proposed first, then validated by observing whether it produces the expected results. Let's use this method to validate what we discovered during our RCA. First, primary and backup paths are not logically equivalent. In addition, New York and New Jersey are treated as one routing domain. Therefore, the routing in Dallas distribute switches can't distinguish the New York and New Jersey. Therefore, at DIS2, BGP best path is determined by eBGP. Traffic exits through New Jersey. As a result, routing asymmetry. So, key takeaway. The real issue is the architecture flaws. One is the architecture flaw that the two redundant paths are not logically equivalent. The other is also the architecture flaw that the BGP design wrongly treats the New York and New Jersey as same routing domain. These are the two root causes that come together, leads the asymmetry issue. Here, possible design improvements. Option 1. Improve path equivalence through WAN redesign. For example, both paths are New York to Dallas. Option 2. Separate New York and New Jersey into distinct routing domains. For example, New Jersey assign BGP AS300. Option 3. Implement both changes.
You might be wondering, what is the best practice design for the WAN architecture between the headquarters and the data center? As shown in the diagram, the best practice design is something like this. Headquarters connect to each data centers directly, either through physical links or through logical links. Dedicated WAN routers should be used to terminate the WAN circuits. Importantly, the modularity design principles should be applied. It means the headquarters, each data centers, and the WAN fabric itself are all treated as different modules. Inside each module, IGP such as EIGRP, OSPF is used. Inside traditional WAN fabric, iBGP can be used. Inside SD-WAN fabric, OMP is used by default. Between modules, eBGP is usually being used. In this episode 4, we solved the mystery of the routing asymmetry by asking what and why, and by taking architecture design into our consideration. More importantly, by solving the problems, we build up the architectural thinking. In next video, we'll do this one more time to solve another common issue. MS Team breaking at large-scale meeting. If you have questions about this case study, please leave your comments below. Don't forget to click the like button and subscribe to stay updated with the series. Thank you for watching. I'm Ray, and I'll see you in the next video.